Hi guys, welcome back to another episode in our Intro to Calculus series. Today we're going to be taking a look at the second derivative. Now, the second derivative has a bit different notation, so it's, well, remember how we said that f prime of x represents the first derivative? Well, you can just do f double prime of x to represent the second derivative of f of x. Another notation using the dy dx notation, you can write dy squared over d squared x. Both of these are acceptable, but well, when we introduce the idea of the second derivative, we're also introducing the idea of the third, the fourth, the fifth, and the nth. So you can imagine that this notation kind of falls off after the third derivative, right? You really want to start to use this notation when you are dealing with, like, say, the 100th derivative. And this is just because you're going to take up too much space doing this sort of notation. So this is preferred when you're doing really big derivatives, and you probably won't be dealing with those at this level, but it's very possible that in your future you will be needing to, say, take the 100th derivative of a function, and because and it's not going to be you're differentiating 100 times, you're looking for a pattern, for instance, but this is the notation to represent the 100th derivative. So now that we know the notation, let's talk a bit about what it is. So really we're just differentiating the same function twice. So we're taking the derivative of the derivative. Let's look at an example. If we have f of x is equal to x cubed, the first derivative using the power rule, we drag the 3 down, subtract 1, then we get 3x squared. That's the first derivative, and we're going to take the derivative of this function with respect to x. So drag the 2 down, 3 times 2 is 6, and then subtract 1 from the exponent, you get 1. Our next example is a bit more tricky because it's 1 over x. Now, the first derivative is negative 1 over x squared. This is because you can imagine this function, instead of looking at it as a fraction, look at it as x to the negative 1. When you do that, you're going to imagine dragging that negative 1 down from the exponent, and it drags here, and then reducing that negative 1 by 1, so it becomes negative 2. So you have negative x to the negative 2, and that, of course, becomes negative 1 over x squared. Taking the derivative of that again, you're going to look at this as negative 1 times the derivative of x to the negative 2. So you're going to drag that negative 2 down. It's going to times this negative 1 to make 2. And then you're going to reduce the degree by 1. So you have x to the negative 3, which gives you this as your second derivative. Our last example is one that, again, reiterates the, well, a bit of the interesting nature of derivatives. We're going to explore the idea that the derivative of something can equal 0 and when it's equal to 0. So if we have the function is equal to a linear function, right? We imagine a linear function as this. The rate of change or the slope of that function is going to be a constant 17, right? And what does the second derivative really represent? It represents the rate of change of the first derivative. And if our first derivative is a constant line, like this, right? This is 17, for instance, on that like xy scale, you have this line as being y equals 17. It's not changing, right? It's always going to be, regardless of what, where you look on the xy axis for that f of x graph, that line is not going to, it's always going to stay as y equals 17. You cannot get it to increase at all, which is why that rate of change is 0, because it doesn't matter if you shift the x by a tiny bit, the y doesn't react at all. And that's going to be our final example for this introduction to the second derivative. I hope this helped you guys understand what it is and get a grasp on how you deal with problems that ask you to take the second derivative. If you have any questions or comments, please feel free to let me know. Alright, thank you for watching.